All right. Hello. I'm going to go ahead and get started. My name is Julius. I'm going to be presenting over the next 20 or so minutes my work from the semester in the biorobotics lab with Ananya and Professor Howie Choset. The work is titled Spectral-Based Decentralized Allocation for Heterogeneous Multi-Agent Coverage. Over the course of the presentation, I'm going to do my best to unpack that word soup and to give some motivation and background for the method, and then we'll dig into the actual function of the method and show some preliminary results that we have as well. So let's get into it. All right, so search with multi-agent teams is a very active research area with many applications. On our planet, a popular application is search and rescue, where teams of robots or agents must collaborate in order to find a target. And on other planets, a popular application is robotic exploration, in which case, sort of, we also benefit from having teams of robots collaborating on a task. In many of these tasks, coverage benefits from having agents with different abilities. So different abilities can come in the form of different kinodynamic profiles or sensing profiles. And what that means is sort of we benefit from having agents that move and sense in different ways. For example, in a search and rescue operation, we could benefit from having UAVs and quadrupeds. So UAVs will have a broader, lower confidence sensing footprints. They'll fly higher up, they'll see more, but with lower certainty, while quadrupeds will have a much more localized, sort of high confidence sensing footprint. They will move slower, but they will sort of see what they see around themselves with much higher confidence. And so we have a benefit to both. If we take a hypothetical search scenario where we're doing a search with a heterogeneous agent team in a forest, let's say that we sort of have a forest, we have a path, we have a field, and we know that our target lies most likely somewhere along the path and with a lower probability somewhere in the field. Now, note that sort of in order to conduct the search, we need some information prior. We need some prior understanding into as an input into the system, which dictates sort of to the algorithm or to the distribution of agents where we want agents to distribute proportional to the density or probability of finding a target in a certain region. Now, looking at this example, we have the path, which is a localized high information density region, and then we have the field, which is a more distributed low information density region. And so for you and I, intuition might say, well, if I have a quadruped and a UAV, I might dispatch the quadruped along the path, and I might dispatch the UAV into the field. And if we actually unpack that intuition as to why we sort of jump to that conclusion, well, perhaps it may be because the path is more localized, and so the quadruped will be able to see better, sharper along that sort of small area or proportionally smaller area, while the UAV will be able to cover the broader field, which sort of is much more area. Perhaps it doesn't make sense to have the quadruped trotting through the entire field slowly, while the UAV could just zip around and cover it much faster. Okay, so that's sort of one example. And so the goal of the method and the motivation behind the work is to actually formalize this intuition that you and I might have into a more formal method to allocate agents for scenarios like this and many others. So more formally, we seek to minimize the divergence between the information and the sensing distribution. The information distribution being our prior, and the sensing distribution being the distribution sort of that the that the agent team has when it senses the environment. And so if we take a sort of pretty trivial example and we take a bimodal information distribution where we have two densities, one which sort of both are Gaussian and it's normalized overall, and one is sort of clearly much sharper and much more peaked, and one is sort of more distributed and with higher variance. And we take two agents and we distribute them to cover the information distribution like so. So you also see two peaks. The sharper peak could, for example, correlate with a quadruped, which has a more localized sensing distribution, and then the sort of more distributed peak might be something more like a UAV. Now, when we look at these two, we see a mismatch. And the mismatch comes from the fact that sort of the agents are not well matched to the regions that they are covering. And mismatch in sensing and information distributions leads to worse coverage, and that's something that we seek to minimize. So we seek to minimize the difference between the two by manipulating the distribution of our sensing agents. So then that begs the question of how can we best align the agent sensing distribution with the information distribution that we seek to cover? One option is comparing sort of the position of the agents and their sort of corresponding sensing distributions in the spatial domain. But there is a drawback with this. when you are comparing the sensing footprint of each agent and the information distribution that you're seeking to cover, and you do so in the spatial domain, what you will end up doing is penalizing every tiny difference between the two distributions spatially, which we don't necessarily want to do. So if we have a sharper peak, we don't want the agent sort of that's assigned to that sharper peak necessarily just staying within its center, for example, just to minimize the spatial divergence. We actually want it moving around that peak. So I guess more formally, we want to actually match agents to the properties of the peak rather than the sort of spatial characteristics of it on its own. And so that's why we actually do things in the spectral domain. The spectral domain is a really good candidate for this task. I'll sort of touch on why. So if you consider an information distribution, and we sort of see broader features will correlate with lower frequency spectra. And sharper features will correspond with higher frequency spectra. And so if we actually analyze that, we will do more towards actually matching agents with the properties of their sensing distribution, with the properties of, or the structural features of the information distribution, rather than nitpicking at each sort of individual difference between the two. And so that's motivation for why we actually end up doing things in the spectral domain, and we'll go into how we do that now. So an introduction to the method. We present a framework to allocate heterogeneous teams to match agents with regions of the environment best suited for their sensing profile. Now, a key aspect of the method is that we don't rely on explicit inter-agent coordination, and so the result is that the method scales quite well with team and environment size. We also present a framework to do online reallocation of agents in response to evolving information distributions. And so we'll talk about why distributions or underlying distributions would evolve and why it's important for the method to be able to respond to that on the fly. So the method has several components, all of which we will cover. So the first is, okay, well, given some continuous information distribution, I need to somehow discretize it. I need to somehow sort of decompose it into manageable regions within which agents can operate. And so we call that sort of a high-level graph into which we decompose it to. We define a method by which agents decide to transition through the high-level graph, and we define a method to evolve the graph online to shifting underlying distributions. So to start, let's talk about this graph. Let's talk about sort of why we need it, how it comes about, and how it looks like. So when we have perhaps really, really arbitrarily large continuous information distribution, we want agents to be able to sort of focus on local regions without having to worry about the rest of it. And that actually makes it quite amenable to having the whole framework be decentralized, because you don't need sort of to have explicit sort of agent knowledge or coordination of the global team state or the global information distribution. Our method only relies on local knowledge. So in order to decompose a sort of arbitrarily large density, we sort of find that Gaussian mixture models are really sort of a really good candidate for that. So Gaussian mixture models are universal density approximators given a sufficient quantity of components. So if I have some density and I collect these samples from the density and I fit a Gaussian mixture model with 3 components to it, perhaps it'll look something like this. And sort of they would have different weights as well, corresponding to the density or proportion of the density that they contain. So each component, arbitrarily call it K, will be parametrized by a mean, a covariance, and a weight. And so these define the components and the mixture model as well. So it may start to come together sort of how we're actually decomposing the continuous density into these distinct regions. Now, there is a problem with Gaussian mixture models, or just the vanilla version, and they suffer from having to specify the quantity of components that you want to have a priori, so sort of prior to actually fitting the model. And that's not ideal because, first of all, you'd be guessing. And second of all, sort of it's a parameter that we can we like to avoid if we can. And we can just by sort of having a slight addition. So Dirichlet process Gaussian mixture models don't require specifying the quantity of components a priori. And so that's what we end up using. An example of why sort of that would be useful is if we resample from a new distribution and all of a sudden we have this sort of new red mode, and we still try to fit a Gaussian mixture model with 3 components, all of a sudden you can see that, yes, it does fit to it, but it's not appreciating the sort of multimodality or different modes within our distribution quite as well. Now sort of it's assigning 1 Gaussian to 2 individual modes that we see within the distribution. Okay, so we talked about how to decompose a continuous information density into individual regions. Graphs need to have 2 components. They need to have both nodes and edges. So sort of there is a question of how do we best connect components in the high-level graph? The approach that we take is motivated by two ideas. The first is intuitive. It's preferable to have spatially proximate neighbors to minimize travel distance when agents are transitioning, if they can only transition along nodes as we specify. The second is perhaps slightly less intuitive, but I'll do my best to go through why we sort of came to this conclusion. It's preferable to have neighbors of diverse spectral composition. And this maximizes the connectedness of the graph experimentally, and also experimentally better avoids agents getting stuck in local optima and actually not transitioning as well or propagating through the graph as well as we'd like to regions which we sort of know that they would be better matched to. So take an example, and we'll take a look at several edge creation strategies that we considered. So we have just a sample map with 6 Gaussian densities and sort of normalized to one distribution. And we go ahead and we call each of them a node, and then we draw edges between them. So the one on the very left is just random edge creation. And again, we want to maximize the connectedness of the graph. We want agents to be able to get to every node or as many as possible through our graph. And so sort of the random approach does actually relatively well experimentally, but it's unreliable. So it does well sort of when it just happens to come together well, and then when it doesn't, it really doesn't. Now, another approach that you might take is say, okay, well, I might want to draw edges to the neighbors with the lowest mean power spectral density. And those are sort of the neighbors here with the highest sort of covariance. And so what you will see is that from the nodes that have a much sharper peak or a lower variance, all of the edges are actually emanating out to the higher variance neighbors, and none are actually coming back. So if we initialize, for example, all of our agents, which we don't always control the initialization sort of strategy or locations in our task, then we actually, if we initialize only the higher covariance neighbors, then we don't actually end up having sort of agents propagating to the lower covariance, sharper peaks within this distribution. And that would be a huge problem in aligning the sensing and information distribution. You see the opposite is true with doing the opposite approach, with taking neighbors with the highest mean power spectral density, and you run into sort of kind of an opposite problem with taking neighbors with the closest mean power spectral density. And so with our approach, where we connect one neighbor to the highest neighbor, neighbor with the highest mean power spectral density, and a neighbor with the lowest mean power spectral density, we see that the graph reliably is well connected, and agents experimentally are able to pretty well propagate throughout this graph and align with the underlying distribution. Now, this example is considering 4 nearest neighbors in edge selection. So we take our 4 nearest neighbors and we choose which of the 2, in this case, we sort of draw edges to. Now, the formal approach that we take is we take the k nearest neighbors and we draw the edges to the neighbors with the highest and lowest mean power spectral densities. Now, you might ask, well, why 2 edges? And that's a great question. This is sort of more of an art than a science. And so with more edges, we found that experimentally, this results in more oscillation within the system as the agents work to converge to a better sensing distribution. And having sort of too few edges will result in insufficient connectedness for the agents to actually well propagate throughout the graph. So 2 is a sweet spot, but sort of this is definitely sort of a potential topic for future work. So let's see it in action. So given some distribution that we are given like this, we can fit a Gaussian mixture model, and you'll see that sort of it's a good approximation. It's most certainly not exact, but when we actually trace out our edges, the graph ends up actually being really well connected, and it would allow agents to propagate through the graph really quite well. And so this is an example of the traversability graph that we would end up looking at when we seek to sort of have agents decide where they're going. Now, we have our graph. Let's talk about how agents actually conduct these transitions or actively decide to transition through this high-level graph. So we operate within these sort of regions that we call regions of interest. Regions of interest are triplets of nodes in the high-level graph, consisting of a central node and the 2 nodes that it has outgoing edges to. we assume, in terms of what we think the agent knows, we assume that the agent has knowledge of the subset of the team that it has within its node, and the subset of the team present at the two adjacent nodes. So within this region of interest, we assume that it knows the composition of the agent subteam and also the structural properties of each node. Now, the goal is to have agents independently optimized for the agent distribution to locally match and see that sort of this local process actually ends up evolving into this global alignment that we seek. And so this would be sort of the region of interest in this case. Now, let's talk about sort of graphically and intuitively before we sort of go into actually how this works on the back end. So given this region of interest and given two distinct types of agents, so given that we have this agent subteam formed in this region of interest at time step t, let's say that we run an optimization which each agent would be doing independently, and we find that this is the desired agent subteam distribution at time step t plus 1. An important thing to note, and let's give these nodes sort of more formally titles, so A, B, and C. With this process, we are only asking how can the agents at time step t at node A best transition in order to align themselves with the local distribution? How can they best transition or stay put to nodes B and C? So we are not looking or assuming that sort of the agents at nodes B and C will be reciprocal in their movement. We don't assume that at all. But actually, by conducting this local process sort of iteratively, we find that it leads to a global convergence. And sort of, you might ask, well, why don't we assume reciprocal movement from agents B and C? And the answer is because sort of node C, for example, has two of its own neighbors that it has outgoing edges to. And so it will be doing this optimization process sort of on its own as well. And so how to actually best schedule these transitions to optimize convergence is definitely a topic for future work. But the result is that we're only asking the question of at agent, sort of the subset of agents at node A, how can they best act to align themselves locally with the distribution, but sort of not assuming or having agents at nodes B and C act reciprocally. So given here, we would say, all right, well, this blue agent would sample a distribution saying that, well, ideally, there's one blue agent at nodes A, B, and C respectively. And so agents at node A would have a 1/3 chance of sampling a position at each node. The pink agent may say, okay, well, I optimized over some criterion of the local spectral divergence. And I may say that sort of 50% should be at node A, and then 25% should be at nodes B and C, respectively. And so I'll have a 50% chance of staying put and a 25% chance of moving to nodes B and C. Now, note that sort of we don't want agents to be doing this at every time step. That would result in pretty sort of intense oscillation, and it would experimentally, we find that is a huge detriment to the actual search performance because it's actually really hard for the agents because of these like local processes to globally converge reliably. And sort of it would take a lot of iterations. So we look for some improvement. And the way that we actually reduce oscillation is by saying, okay, well, these transitions are only going to happen every X time steps. They're not going to happen at every time step. We're going to say, let's say every 2 minutes, the agents have an opportunity to transition. They run this local optimization, and then they choose whether or not to stochastically transition. And over time, we see a better alignment with the underlying distribution. So the final component is this online evolution of the high-level graph. We want the high-level graph to evolve over time in response to shifting underlying distributions. The underlying distribution may shift, for example, because agents may exhaust local optima, or because new information is introduced that we now want agents to cover as well. So recall that within our Gaussian mixture model, each component, call it K, is parameterized by a mean, a covariance, and a weight. And so the mixture models actually allow for a very intuitive evolution of parameters by sampling from this new distribution and conducting updates to the parameters via an expectation maximization approach. And so I'm throwing up formulas here, not sort of precisely with the hope that sort of it's fully understood, but rather to just see the flow that all we're doing is taking the parameters from the previous time step, and we are updating them via sort of a learning rate hyperparameter that is defined. And also we use the sort of function rk of x, which is defining the posterior responsibility of component k for point x. But the general idea here is that we are updating the parameters given new samples from the underlying distribution. Now, Um, we will have sort of as a result over time, the Gaussian mixture model is going to be updating its parameters continuously. But at some point, we're actually going to cross. We don't want to be updating it continuously as well, because that's sort of a pretty large computational burden. And we don't want to be continuously reallocating agents or having to worry about agent responses to this sort of shift in the high level graph. So we say that, okay, we're going to actually update this high level graph once the change in the parameters crosses some threshold delta, which is arbitrarily defined. And so this sort of shift in parameters is defined by the change in both the means and the covariances of the different nodes in the high-level graph. And so if an update is triggered, we can expect one of several outcomes. The first is to have node shift, and that's if an existing node K will exhibit sort of a delta K greater than this arbitrary delta. And so the nodes with incoming edges to node K will reevaluate their edges to see if sort of they want to actually move some of their edges around. We could have a new node that's introduced. If the Gaussian mixture model introduces a new node with sufficient weight, then the node will be introduced to the graph and its edges will be assigned. And then the nodes within the immediate regions that sort of fall within the K nearest neighbors will also reevaluate their edges. The final case is node removal. So this you can expect if you've sort of exhausted a local optima, for example. And that will happen if the Gaussian mixture model updates the component weight to be too low or lower than our threshold. And so the node will be removed from the graph, and the nodes with the incoming edges to the former node will now have to reevaluate their connections, and the agents that were previously within that node will have to be reassigned. Now, note here that the updates remain really local. So we sort of don't require agents in a completely different region to actually sort of respond to these updates, local updates within the high-level graph. They don't even need to know about it. And so this, again, sort of goes towards the scalability of the method towards sort of varying sizes of distributions or environments that you're operating in. So a few experimental results as we wrap up. I know I have a few minutes. So this is an example where we have a UAV and a quadruped conduct a weighted random walk with active allocation. So you'll see that sort of we start them in these different regions, and then they will actually sort of stochastically choose to transition. You can see the transitions between the nodes over time. Now, you can see that these transitions are actually presenting quite a bit of overhead to the search performance, or perhaps you can't sort of see it as much as perhaps intuit it. But for the quadruped, which is relatively slow moving, moving between the nodes actually presents quite a bit of overhead that detracts from its search performance. Now, experimentally, this sort of detriment goes down with team size because you generally have fewer agents moving in between nodes to realign, but this was sort of definitely a topic for future work on how to best handle that. We compare against several baseline search strategies. Now, when we say sort of baseline search strategies, it's important to note that once an agent is in a node within this high-level graph, it's not just remaining static. It is moving around and it is searching, but we don't define the method or strategy that it has to use in order to conduct that search. So that actually makes the framework quite generalizable. So when we compare sort of the performance of a few baselines like weighted random walk or ergodic search or sort of greedy search, we find that the active allocation actually significantly improves the performance of the methods, particularly in allowing agents to escape the local optima that they end up exhausting relatively quickly. So for future work, we're looking in several directions. The overall goal is to improve the quality and speed of convergence, but we look at doing so by, first of all, improving the scheduling of transitions. Right now, it just sort of happens completely disjoint for each sort of local region of interest. And also accounting for agent kinodynamics and looking at sort of, okay, well, a quadruped would perhaps be better aligned over there, but if it takes sort of, I don't know, 3 hours for it to get there, perhaps a UAV could just sweep in and spend an extra little of time, sort of amount of time there to compensate for its suboptimal sensing footprint. And so looking sort of and incorporating that, that's not currently included in the method and definitely is something to look into in the future. So that concludes